Semyon Dyatlov from MIT. We'll talk about control of eigenfunctions on hyperbolic manifolds.
Yeah, so I'd like to thank the organizers for inviting me to speak here. I'm going to talk about something called control of eigenfunctions. Some of those results are on the older side. I'll try to focus on the newer results, which are in higher dimensions, but inevitably I will have to review the two-dimensional case first. So let me jump right into it. So here's the setup. I will have a compact Riemannian manifold throughout the talk, and then I'll be studying Laplace eigenfunctions. And specifically, I'll be studying the high energy case. So I'll take a sequence of Laplace eigenfunctions where the eigenvalue is going to be lambda j square. I'm not sure why I should apologize for calling eigenvalue lambda square. Really, my Laplacian is sum of partial x j squares and flat space. I will justify this, but lambda j will go to infinity. So okay, what's lambda j? Lambda j is the frequency of oscillation. And then I'll normalize them in L2. This is going to be a completely L2 based talk, so normalize them in L2. And then I will also have a semi-classical parameter, which I'm not going to apologize for either, which is lambda j inverse. And what's that semi-classical parameter? It's the wavelength of oscillation of the eigenfunction. So it's a scale of the fine features of the eigenfunction. And so that one will go to 0 as my eigenvalue goes to infinity. Now there's many questions you can study. Some of them have been already mentioned or addressed before in this conference. But for this talk, I'm going to stick to a question of macroscopic behavior of eigenfunctions. So you can imagine that I have some eigenfunction that oscillates a lot because it's high frequency. But then I want to step back and just study its behavior on sort of macroscopic sets. So I'm not rescaling my eigenfunction. I'm not looking at it at wavelength scale. I'm looking at it at scale 1. And then I'm sort of averaging the mass of this eigenfunction. And so a typical way to study those is using something called semi-classical measures. Not roughly half of you are familiar with those, so I'll introduce them, but very quickly. So this is done using something called semi-classical quantization, which I'll write here once, and of course in the actual proofs you have to work with the subject a lot, but generally I'll try to stick to pictures in this talk. But somehow when I draw pictures of micro-localization, I mean that I use this technology inside. So what's a semi-classical quantization? I can start with a, let's say, compactly supported function on the cotangent bundle of my manifold, and then I can map to it a family of operators where h is again this semi-classical parameter, which you can think of as taking it as a function of x and minus ih partial x goes in place of the cotangent vector, and that's going to be a family of operators on L2 of the manifold. Okay? And I use this quantization. And then you can introduce semi-classical measures. So we say that the sequence of eigenfunctions converges to mu, which is a measure on T star m, so on the phase space of my system, if the following statement holds for any symbol, for any classical observable, for any compactly supported function on T star m, this expression, up hj of a uj, so the inner product, converges to the integral of a d mu. Okay? So there is a physical interpretation of this. It's really inspired by quantum mechanics. That if you imagine a free quantum particle living on your compact Riemannian manifold, then the UJs are pure quantum states of that quantum particle, right? They give you time harmonic solutions to the time-dependent Schrodinger equation, and that's sort of how I'd like to think of them. And H is, well, in principle, a Planck's constant, except this one is dimensionless. Then this expression here, this inner product, it's quadratic in Uj, and it's nothing else but the average value of the classical observable A. So T star m here is the space of position and momenta of a classical particle on my manifold. Then A is a function on this phase space, so that's a classical observable. It's a function of position and momentum. Then this expression on the left, a physicist would call it like this. If you ever took quantum mechanics, okay, I'm not going to use that notation. There's nothing wrong with that notation, but that's not one that I'm used to. So this is just the average value of this classical observable on this quantum wave function. And then you want this to converge to the integral of A d mu as the energy, or as the frequency goes to infinity. Okay? So that's this macroscopic limit. I want to understand that position momentum distribution of my quantum particles as the eigenvalue goes to infinity. All right. Well, I guess I can use this to erase. Okay. So that's this by now classical definition in quantum chaos, and I will say such mu are called semi-classical measures. Okay. Okay, so you have a whole sequence of eigenfunctions that might or might not converge. Then turns out you can always find a subsequence that converges to something, and so you can study all possible subsequential limits. So mu is a semi-classical measure, means it comes from some sequence of eigenfunctions. Okay, so those encode different ways in which eigenfunctions can concentrate in position and momentum space. Okay. So what do we know about those semi-classical measures? So I'll review a few of standard properties of those, and then I'll review also some history of the study of that. So what are these semi-classical measures? Well, first of all, they exist. As I mentioned, there is a compactness statement. Any sequence has a subsequence that has a limit. It's very analogous to the notion of weak probability. Of weak limit in probability. Okay, and so this is analogous to, I think, what's called Halley's theorem, which is a weak, compactness of measures with respect to weak limit probability measures on a compact space. Next thing is that the support of each semi-classical measure is inside the co-sphere bundle. And that has to do with how I normalized. The fact that I took Hj here, which is related to the Laplace eigenvalue. So they oscillate. Once I rescale my frequency so I have this big frequency at which eigenfunction oscillates, it's lambda. Once I rescale my frequency by lambda, my eigenfunction oscillates at frequency 1. Okay. Yeah. Sometimes for other audiences, I give a few examples that you can really see this easily on an example of the torus. So if you've never seen this before, think about a two-dimensional torus. You have e to the ikx and e to the iky, and both of those will give you some measures. They will have different frequency localization, but they will have the length of the vector will be 1. Okay, what else do we know? Well, okay, it's a probability measure. Roughly speaking, just take A equals 1, just corresponds to the normalization there of the L2 mass. And then, what's more fun is that these measures are invariant under the geodesic flow on my manifold, and I think of this as a flow on the co-sphere bundle. Right? So here you have this first glimpse of what we sometimes call a classical quantum correspondence, because we have a quantum object, which is a semi-classical measure. It tells me how a pure quantum state would localize at high energy. And it is related to a classical object, which is the geodesic flow. So here you think, what's the geodesic flow? It's the straight line flow. Since I'm in Newton Institute here, it's Newton's first law if you live on a Riemannian manifold. So you're just moving in a straight line. And in order to define this flow, of course, you need to know the initial position and initial velocity, but you can encode velocity by momentum instead. I'd like to believe Newton would have liked it, though we can never be sure. All right. So you get this situation, and so you get this big zoo of measures, potentially, and you know they're all invariant under the geodesic. Now, so from now on, I will assume that my manifold has negative curvature, so negative sectional curvature. I'll write a scale less than 0, but I always mean sectional curvature here. And that's the assumption that will persist throughout the talk. And the way this assumption is used is that the geodesic flow has a stable-unstable flow decomposition, also known as having the Anosov property. So you can decompose the tangent space to the phase space of the flow as the flow direction, and then the stable or the unstable and stable spaces. So these are continuous subbundles of this tangent space. And then you know that if I take d phi t, it expands exponentially on the unstable space and contracts on the stable space. Okay. So that's the property that I'll use. All right. Now, what is known for such manifolds and semi-classical measures in history? So, the first result about semi-classical measures in this context is something called quantum ergodicity, which I'll abbreviate as QE. And that one is due to, well, the first proof was provided by Zeldich, and there was a proof by Coulomb-Verdier. But the Russians, of course, were there first. The theorem was stated by Schneerlin in the 70s, and then the proofs, at least in Western literature, came in the 80s. So let's say 70s, 80s. And what it says is the following. Under this negative curvature assumption, in fact, under much weaker assumption, most eigenfunctions equidistribute. So there is a density 1 sequence converging, so density 1 sequence of eigenfunctions converging to what's known as the Liouville measure, which is basically just the volume measure on S theorem, okay, with correct density and normalization. Okay? There is one invariant measure like that. That's called the Liouville measure. Okay, so most eigenfunctions, what we would say, equidistribute. The probability of finding a quantum particle in some space, set in position momentum becomes proportional to the volume of that set. Now, what about the rest of the eigenfunctions? So there is a quantum unique ergodicity conjecture. And, well, it was conjectured in the 90s. It was conjectured by Rudnik and Sarnak, and then it was, the conjecture states that mu L, so the Liouville measure, is the only semi-classical measure. Which by this compactness statement is equivalent to saying that the entire sequence of eigenfunctions converges to this Liouville measure, so all eigenfunctions equidistribute. That's a quantum unique ergodicity conjecture. It is quite open. There were some arithmetic situations where it was proved, notably by Lindenstrauss in 2006 on arithmetic hyperbolic surfaces. But in general, the conjecture is very much open. So a lot of basically all the results that I'll state from now on would be implied by that conjecture. So if somebody proves QE, then no, that would sort of, you could erase a good chunk of the history of that corner of quantum case. But so far, no proof is available, so we do what we can. So what we can do is prove various restrictions on possible semi-classical measures. So maybe we cannot show that the whole sequence of eigenfunctions will converge, will really equidistribute by volume, but okay, if it converges to a measure, how bad can this measure be? So the first such restriction came in the form of entropy bounds. So that was, say, the late 2000s or early 2010s. And that was the work of Anantaraman, and then Anantaraman, Nonnenmacher, and Gabriel Rivière, and Anantaraman Silberman, among other people. And what it basically says is that, well, there are different papers, with different results, but one result that's particularly nice is this result of Anantaraman, Nonnenmacher, which is the entropy, the measure theoretic entropy of the measure is bounded below. Okay, there are various caveats to that, but this is not an entropy talk, so I'm not going to go into that. So in particular, if M is a hyperbolic, so I'll state one thing. If M is a d-dimensional hyperbolic manifold, what they showed is that the entropy is greater or equal than d minus 1 over 2, which is half of the maximal entropy. Okay. So in particular, it rules out half of possible semi-classical measures in some sense. It rules out, for example, a semi-classical measure, which would be a closed measure on a delta measure on a closed geodesic, because such measures would have entropy zero. All right. So it was a very, very important development. That sort of showed that there is some difference between the class of all phi t invariant measures and the measures that actually come from eigenfunctions. So you can see that some measures are too concentrated to come from a sequence of eigenfunctions. That was amazing. And let's see, is that all with the history? I guess that's it. I might have abridged it somewhere, but now I will present some results that are somewhat more recent. Some are recent, more recent than others. And so I'll start with the results in dimension 2. So I'll say results. So for surfaces. So here is, oh yeah, right. I can say here, so there's different restrictions. For example, you can talk about the entropy of a measure, but in this specific talk, from now on, I will only care, conveniently, about the support of a semi-classical measure. So it's a geodesic flow invariant set. Of course, understanding the support of the measure is, it gives you less information than understanding the measure itself. If pressed, I can provide, some examples of how that's quite different. But understanding the support of the measure does have some applications of its own. So in particular, it's related to the question of control for Schrödinger equation. And it's also related to decay for damped wave equation. So there are some applications of the result I am about to state to those problems in partial differential equations, which do not have to they do not have to actually mention semi-classical measures. So there are some end results you can get from it which are not about semi-classical measures at all. Okay. And for those results, you would only care about the support of the semi-classical measure and not about how it's distributed. Okay, so the first result, or actually the only result I'll present in 2D, is this theorem. So it's due to myself and Jin, and in the constant curvature case, and then myself, Jin, and Nonnenmacher, or Jin, Nonnenmacher, and myself, I'm sorry. in a variable curvature case, and that was done in the sort of late 2010s, which is gonna say assume the dimension of my manifold is 2, and I always assume it's negatively curved. Okay, so I'm not gonna keep writing that, but that's a very important assumption for us. Otherwise, the theorem is actually provably false. So for round sphere, this theorem fails, as it does for the torus. Then our conclusion is that the support of the semi-classical measure is the entire closed-sphere bond. So it's as big as it can be. So if you only care about the support of the semi-classical measure, and if you are content with being on a two-dimensional negatively curved manifold, then this is the ultimate result. Right? It's you can't get better than that, you know, with those caveats. So now I'm going to talk a little bit about the proof of that. Mostly I'll try to draw some pictures, but I'd also like to introduce the main ingredient that's used compared to the previous work, because that's also going to be important in higher dimensions. And that main ingredient is called the fractal uncertainty principle. Maybe I'll be able to wedge it here. So in general, I have this feeling that a lot of those results about semi-classical measures, they can be interpreted as some kind of classical quantum correspondence plus an uncertainty principle. Say for the entropy bounds, use something called entropic uncertainty principle. For this bound, use something called the fractal uncertainty principle. So it's a statement in harmonic analysis, and it's actually rather easy to state. So I'll try to do it on this board. Let's see, where is it? Okay, there you go. So I have to define the statement says that you cannot localize in position and frequency. A function cannot localize in position and frequency in a fractal set. I'll first define what I mean by a fractal set, because that's of course a contentious topic, what a fractal set means. So I'll give my definition, which is this. So if you have a set inside R, which is a set inside a real line, is called nu porous on scale h to 1. So I go down to the wavelength scale if the following holds. For any interval I of length between h and 1, there exists a subinterval j such that it has length nu times the length of I, and it doesn't intersect my set. Okay. So maybe I can draw a picture. Is there color chalk? There is color chalk. Red, green, okay. Let's see how green on green works. But I have my fractal set, maybe it looks Cantor-like, and I take an arbitrary interval. I know, it's hard to see, right, because of the lectern. So I'll try to pull this up. So I take some interval I, and then the idea is that I can take a fixed fraction of this interval that does not intersect my set. Okay, that's a version of being nowhere dense. Okay, so what is the fractal uncertainty principle? Well, the version that's used in that theorem is this result, which is an old result by now.
Sorry, so J is also an interval, or it's any set?
J is also an interval, right? So I's and J's are going to be intervals, and its absolute value is just the length of the interval. That's right. Yes. Which is important, yes. It's not a volume type statement. You really want real, intervals. So okay, what's the fractal uncertainty principle? It's a statement of this form that if I take two operators, so one is localization and position to a fractal set, and the other one, I will pull up the board in a moment, and the other one is the localization in frequency to to a fractal set. So here, localization frequency, I think of it as a Fourier multiplier. So dx is minus I partial x. Okay, so if you think about what this does, that's a Fourier multiplier corresponding to the set y is scaled by h inverse. So it's a high frequency Fourier multiplier corresponding to some fractal set. So I have this product of two operators, one localizes in frequency, one localizes in position. Then I'm going to look at the operator norm of those. And I want this to be small with h. So the idea is that then no function can localize on the set y, or h inverse y really, in the Fourier space, and on the set capital X in position space simultaneously, because if I multiply the two localizers, I get something small. Now, okay, this theorem is missing quantifiers, so of course I'll put them in. So what are x and y? They're any sets which are new porous on scales h to 1. This works for any h positive, but really h small is what we're interested in. So it's asymptotic limit. And then here it's this. For every new positive, there exists c and beta positive. There you go. I think that's a correct theorem actually now stated. Now I can pull this up. Okay. Right, so you fix the porosity constant, sort of tells you how non-dense your set is, and then you recover those constants that tell you how fast the norm decays. Okay, so beta positive, of course, is the crucial thing here, and these constants, they don't depend on h, they only depend on nu. Okay, so now how do we go from here to there? So how does this theorem imply this theorem? So I'll explain it, but again, I'll try to draw some pictures because it's the writing gets a little bit annoying. It ultimately uses a version of what's called symbolic dynamics in in dynamical systems, which is just really beautiful, and this thing that was inspired by thermodynamic formalism originally. But it's a pain to write. If you actually want to write it down in formulas, sort of, you get long formulas. So I'll draw pictures, because that's really what's going on there. So how do I show that the fractal uncertainty principle implies that the support of mu is the entire S theorem? I will restrict to the case of hyperbolic surfaces. So I'll assume that my curvature is identically -1 to, greatly simplify my job here. Well, I'm going to argue by contradiction. So assume I have some sequence of eigenfunctions converging to some measure. I'm not going to write that. And assume that I have a non-empty open subset of S theorem whose semi-classical measure is equal to 0. Right? That's the negation of having full support, means that the measure of some open set is 0. Then I'm going to look at the micro-localization of U. So this is where I will get intentionally vague. So I will look at I'll write it once, micro-localization of U. So of my sequence of eigenfunctions. So the idea here is that you have this semi-classical quantization, and you can take different symbols, which in my case will actually be h-dependent. They'll correspond to sets that sort of shrink with h. You can quantize those symbols to operators, and then you can apply those operators to U. For example, if you get something small, you will say U lives away from the support of the symbol. Okay, so very vaguely. So what do we get about this micro-localization? Well, the first property is that since the measure of U is 0, this means that U is small on this set U, which I call a whole. That sort of follows from just from this statement. You just take a function, support it inside your whole U. The right-hand side is 0. The left-hand side has to be small. You can think of it as norm squared if you do it correctly. So this means that U lives, so it's micro-localized, whatever this means, on S theorem without U. Sort of standard elliptic estimates tell you it lives on S star M, and then without U. Yes, Jerry?
A lot of U on the board. I think you're microlocalizing these capitals. Microlocalization of U.
I'm micro-localizing the eigenfunction.
Microlocalize the eigen. Oh, I see. So you,
The little u is an eigenfunction. It really depends on h, or again.
okay.
I erased 95% of the letters that are needed, but but that's the idea. So imagine I have a counterexample sequence of eigenfunctions. Then in this high frequency limit, it has to live on the complement. In some sense. Now the second statement is a finer version of classical quantum correspondence, which can actually be used to show, for example, this measure invariance, which I haven't erased yet. And so that's something called Yegorov's theorem. I'm not going to state Yegorov's theorem, but it relates conjugation by, let's say, the half-wave group or by the Schrödinger group to pull back by geodesic flow. That's where the geodesic flow really enters the picture. In a way, that's the only place where the two are linked in the argument. So Yegorov's theorem will tell me, plus the fact that U is a Laplace eigenfunction, will tell me that the microlocalization of U is invariant under the geodesic flow. The physical intuition is as follows. If you have an eigenfunction, it's a pure quantum state multiplied by e to the it lambda j squared over 2 h, you're going to get a solution to the time-dependent Schrödinger equation, right? Each pure quantum state gives you a solution to, it has a nice time evolution which doesn't change its mass distribution. So then the Yegorov's theorem will tell you that the way that your quantum particles are localized in position momentum follows the geodesic flow. But okay, if you have a solution here which is time independent essentially, then the localization of that solution in the position frequency space then has to be geodesic flow invariant. So that's the general explanation of why this is true. Now if I combine those two together, you see that my U, it lives away from the hole, capital U. And again, the way it lives, the place where it lives should be geodesic flow invariant. So, okay, it's not in the hole. Where does it live? Well, it has to live on the set of trajectories that sort of never cross the hole. Because if you look at some point where if you take the geodesic flow going out from this point, you're going to cross the hole, 1 and 2 will tell you that U is small near this point. Now, there is a limit to how much we can actually make sense of this microlocalization, given by the classical uncertainty principle. So, what you can show, and even here I'm lying by an epsilon, you can show that U lives in the following two sets. I'll call them gamma plus minus, which are the sets of trajectories. What did I call them? Rho? Why not? Rho in S star M, such that for every t, from 0 to, here I should really put log 1 minus epsilon, but I'll lie and put just the log. So for every t up until logarithmic time, phi minus plus t of rho doesn't lie. So gamma plus is the set of trajectories that do not intersect the hole in future time. Gamma minus is the set of, in past time, and then gamma minus is the set of trajectories that don't intersect the hole in the future time. For some amount of time. That's as far as you can make this argument work. At least as far as I know. Okay, so those are these two sets. And then we're going to study what those two sets look like and see that the fractal uncertainty principle tells you that you cannot actually be localized in both of those sets at once, whether you're an eigenfunction or not. So let me study those sets. Let me draw them a little bit. Oh, well, I'm erasing the stable-unstable decomposition, but I will use it in a moment. Hopefully you still remember what was written here. So what does the set gamma minus look like, for example? So gamma minus, it turns out it is foliated, in some sense, it's rather smooth, by the leaves of the flow and stable equation. Right? So you have those stable, unstable flow decomposition in the tangent spaces of the phase space. Then you can take this stable and flow directions together. That gives you the weak stable space. And that's Frobenius integrable, so you have leaves of that. Okay, you have leaves coming from that. And the idea here is as follows. Imagine I have 2 points. Maybe here I'll use chalk again, color chalk again. So imagine I have 2 points in a star. Let's call them rho and rho prime. And imagine that they are connected by a weak, so they'll live on the same weak stable leaf. Now, how do I determine whether a point lives in gamma minus? I have to propagate forward in time and see if I cross the hole. Right? That's the definition there. Right? I have to go forward in time for some time and see if I cross the hole. Well, so let's go forward in time. And then you will see that those 2 points, they can only get closer to each other. If it was the strong stable, they would exponentially contract to each other. But here, if they started close, then they have to stay close. Right? There's no expansion in this direction. So I'll pretend that they contracted, even. Just like that. So the idea is that if this was less than epsilon, then the distance here between phi t of rho and phi t of rho prime is also less than epsilon. And now if I draw my set U, you will see that either phi t of rho prime are both in U, or they're both not in U. The idea here is U is a macroscopic set, and so the distance here is small, so generally you would expect that if one of those points lies in U, then the other one does as well, which means that sort of the futures of the trajectories are linked together, means that you know, if one of the trajectories is in gamma minus, then the other one shadows it closely, so it should also be in gamma minus. Obviously there is a lie because U has boundary, but that's easily fixable if you allowed me to draw more letters. Okay, you slightly expand it, and that's not an issue. It's sort of a real analysis exercise how to fix that. So it's not literally foliated, but you can think it's sort of made of long pieces, or macroscopic size or epsilon size pieces of this foliation. What about the other direction? Well, gamma minus intersected with an unstable leaf is actually porous. That's key property of that set. And to show that, I'm going to do the following. So I'm going to draw now an unstable leaf. And I have here rho and rho prime. They're connected by an unstable leaf. And then I'm going to run my flow for some time. The unstable leaf will expand. Right? So imagine here that I have the distance between that. Let's say I have an interval inside the unstable leaf. Let's call this I. And the size of I is maybe some alpha. And then I'm going to expand this for a carefully chosen time, so that phi t of I, so that has size e to the t times alpha, and I'm going to make it a fixed large number. So I'm going to choose my direction of my time of propagation in the argument so that this unstable piece is expanded to sort of a large fixed interval. Now what we use is that U is in an empty open set, and sufficiently long, you know, the global unstable leaves are dense. And so global leaves of E unstable are dense. That's a well-known property. This is where we use, by the way, I completely forgot to mention that my manifold is connected. And that's where this would be used. And so then you can see it, because everything is compact, if you take sufficiently large number, capital T there, then every size T segment of a global unstable leaf will intersect my non-empty open set. So you have this picture. And now, I'm going to run backwards. So what will happen is that now I'm going to say, well, with a little bit more work, I can see it contains some epsilon size subinterval. And then when I go back, let's call this phi t of j. And here is my subinterval j. And the idea would be that phi t of j does not intersect u. And then by the definition of those sets, then if you go for time t, you're going to be in the hole. J doesn't intersect gamma minus. And that's a proof of porosity. For each interval, for each unstable interval, I construct a subinterval with fixed size. It's just the size nu is just the ratio of this, basically how small a ball this is, to capital T, which is how far you have to go to cross your open set. So it's a fixed number. It doesn't depend on T, H, or anything else. It depends on u.
Shouldn't we phi t of j is included in u? And that's why.
Oh,
j
sorry. Yeah, that's right. That's right. It's included in u. That's right. I got confused with the complements, which means that, yeah, that's right. You're in the hole. Okay, so that's porosity. And now when you combine those two statements, you will see that I should erase something. Perhaps I'll do this. And I should really get on with higher dimensions. So I'm almost done with talking about the two-dimensional case. Is it a 60-minute talk?
Yeah.
Officially? Okay. So what you can see is that then gamma minus will locally look like R2 cross some set X minus, and gamma plus will locally look R2 the set X plus. So here my R2 is in the weak stable direction, and X minus is in the unstable direction. Right, because you have a set that's foliated by two-dimensional disks, and when you intersect it with a transversal, it's porous. Doesn't matter which transversal I took, because in the other direction it's roughly constant. So then in the correct coordinates, it looks like a product. Okay. And you can do the same with gamma plus. Of course, you reverse the direction of time, so the stable and unstable things are reversed. And so the way it sort of looks is that if I draw gamma minus, looks something like that in the unstable direction. In the stable direction. And gamma plus looks something like this in the stable direction, where the widths of those pieces are h, the lengths of those pieces are about epsilon, and the way those pieces are distributed transversally is porous. And then with enough work, you can show that fractal uncertainty principle implies that no eigenfunction u, or no function u, can be microlocalized in gamma plus and gamma minus at the same time. And so that gives you a contradiction.
Is the transversality of these things a standard dynamical fact? Is that a hard thing to show?
Well, the stable and unstable are transverse, right? That's sort of baked into the Anosov property. It would be pretty hard to expand and contract in the same direction.
Or even homoclinic orbits, right?
Oh, but this is the whole set is hyperbolic.
Yeah.
Yeah. The homoclinic case is more subtle. But here under this negative curvature, you have complete hyperbolicity everywhere. You're probably thinking about something like what Coulomb, Verdier, and Paris studied, which is a dumbbell, which is a surface of revolution. It has a hyperbolic trajectory, and then something comes back, but the dumbbell is not negatively curved, right? It's this other part that makes it possible to construct them. Yeah. So here we're looking at things that are everywhere hyperbolic. Yes?
Yeah, so then do you use negative curvature or just the property?
This only uses the Anosov property. I mean, the proof I presented is constant negative curvature, but you can make it work with just the Anosov property. In dimension 2, which brings me to the question, what happens in higher dimensions? So this is what I'm here to tell you. Let's see. Maybe I will erase this. Will you forgive me if I erase this? It's the most recent part, but that's actually the part that I'm not going to refer to explicitly. I'll just say by the same argument. Or I should also say that in one of the steps that I erased, I lied in a rather substantial way, which is fixed by following Anand Taraman's original entropy paper. Yeah, so there's many lies here, but that's roughly the picture of how the argument works. So what about higher dimensions? Well, first I can make a conjecture. Conjectures are cheap. Anybody can make a conjecture.
Especially if it's wrong.
Disprove it. It's a challenge. Maybe it's wrong, but then, you know. So here's a conjecture. So I'm going to assume that MG is, compact, connected, negatively curved manifold. I'll just put it like that. Then the support of each semiclassical measure is S star M. All right, so that's my conjecture. Each semiclassical measure has full support. Good luck disproving it. Or good luck proving it. We don't know how to prove or disprove this conjecture. But we have some partial results, and that's what I'll present. So there's many problems in higher dimensions. One of the problems is that the fractal uncertainty principle that I stated there is only valid for subsets of R. And the reason is the following. Let's see, will I be able to do it here? Okay, I'll do it here. I'm sorry, I'm gonna be jumping board to board, I suppose. The reason is as follows. So in R2, for example, so the fractal uncertainty principle fails already in R2 because you can take two sets that look like this. X is an h/1 rectangle this way, and then Y is an h/1 rectangle this way. And then the norm of this product, maybe it's not equal to 1, but it's roughly 1. Doesn't decay. The reason is simple. It's just if you take the delta function on a vertical, on a whatever, vertical line I drew, okay? You take the Fourier transform, you're going to get the delta function on a horizontal line. Okay, so you can imagine you can make up an example of a function sort of localized on this rectangle, and then a bunch of, the Fourier transform of that has quite a bit of mass on this other rectangle. All right, so that's a problem. And of course, you could argue whether a line is a fractal set, but it is ball porous. So a line is porous on balls. If I take any line, if I take any ball, I can take a subball of half minus epsilon, if you want to be pedantic, diameter, that doesn't intersect the line. Okay? So it's a problem. And there is a solution which is, in a way, almost as good as a partial solution can get, which is the following. I think I'll erase some of this now. So here's a theorem. Let's see. I'll have to do it carefully, because I'll just revise this here. So this one is due to Alex Cohen in 23, which is, okay, the quantifiers are the same. For every nu, there exists C beta. And then here, it turns out that you can still make this argument work, or the theorem is true. It's not the same argument, but the theorem is true if you assume that, okay, one of your sets can be ball porous with porosity nu, and the other set, however, has to be line porous. And what do I mean by line porous? So Y is line porous, means that for any line segment, so for any line segment, I'll just write segment, I of correct size, there exists a point in I such that the ball centered at this point of size nu times the length of I doesn't intersect y. So the picture would be like this. I take an arbitrary I here, and then the claim is then the condition is that there exists a point so that a ball centered of this point of some fraction of the length of the interval does not intersect your set y. Okay? So a line is not line porous, right? Because I can take I to be the line itself, and then again, good luck finding a point on the line so that the ball doesn't intersect. Okay? So that's what Cohen did, which I thought was quite amazing as far as the fractal uncertainty principles go. And with that theorem, you're actually able to get at least some partial results towards the conjecture. So you have to be smart because the theorem is, there's many problems in higher dimensions. But there are some settings where you can actually say something. And so here's one theorem, which is due to my student Elena Kim and Nick Miller last year, which is as follows. So I'm going to assume that MG is a compact connected hyperbolic manifold of any dimension. Okay, so that's constant negative curvature. That removes, there's sort of three difficulties with proving the theorem. That removes two of them. But it leaves the difficulty with the fractal uncertainty principle not really being valid. So the support of any semi-classical measure, so they cannot show that it's everything. But what they can show is they can sort of identify possible obstructions. So you can show that the support will contain something, and that something is a cosphere bundle of sigma, where sigma inside of M, and now I'll write it as abbreviations, compact, immersed, totally geodesic submanifold of dimension at least 2. Okay? So it turns out that the obstructions to making the proof work, I stand by the conjecture. I think those obstructions shouldn't actually be there, but I can't prove why. The obstructions to making this work are given by compact totally geodesic submanifold. So for example, if you're in a hyperbolic 3 manifold, then the obstructions will be given by compact totally geodesic surfaces, and people have studied in some cases there is countably many such surfaces, in some cases there are none, but that's sort of a separate question. Yeah. So you get one of those. Now, how do you prove a statement like that? Well, some part of this, yes?
Were there like examples of manifolds where you know the conjecture already? That this condition?
Yes, that's right. That's right. That gives you some examples, because there are some examples of compact 3 manifolds that are hyperbolic and have no totally geodesic surfaces. Okay, compact totally geodesic surfaces. So how do you prove this? Well, some of the strategy above is used, and it uses Cohen's fractal uncertainty principle. But there is a caveat. So Cohen's fractal uncertainty principle needs one of the sets to be porous on lines. Okay? Now here's a picture that I didn't erase, luckily, which is how we prove porosity. And this picture can be used in higher dimensions, at least for hyperbolic manifolds, to prove porosity on balls without any assumptions for any non-empty open set U. Because what you would do is you would take a ball inside an unstable leaf, and then when you expand it, you're sort of covering the whole global unstable leaf, and global unstable leaves are dense. And so if you blow up this ball enough, it's gonna intersect by an empty open set, and then you get a sub-ball, and then you pull it back. So it's the same argument, but it's just with balls. So ball porosity is true here for any non-empty open hole U, but it's not enough, as the counterexample shows, right? To get fractal uncertainty principle. If you want line porosity, then you have to do something else. So imagine, say, you have a hyperbolic 3 manifold. The unstable space is 2-dimensional now. And now instead of taking a ball in the unstable space, you take a line segment in the unstable space in some direction, and then you blow that up. And so that will not necessarily be dense. And so it turns out that you need U to intersect, so for the argument to work, you need U to intersect the closure of each unstable line. And luckily for us, those closures, or luckily for them really, are classified by Ratner theorem. There is some work involved, but that's using sort of some big tools from homogeneous dynamics. You can actually see what those closures would be. Typically, those closures would be everything. And then the atypical cases, with some work you can see, are given exactly by those surfaces. The easy direction is that each such surface will give you an orbit closure, or something containing orbit closures. But Ratner theory tells you that this is the only problem that can occur. Okay?
What is an unstable line?
So unstable line, the way you should really think about it is, that's right, so you go to the frame bundle, and then it just, what does it mean to fix a line? You can see that this line porosity doesn't actually depend on changes of variables much. Because a parabola still looks sort of, when you take a parabola and you zoom in, it looks like a line. So you can pick which line, so you just have to pick a point in the direction for the line. And so on the manifold, so you have to pick sort of a point on the manifold and then an unstable vector. Well, if you think about what it corresponds to geometrically, picking a point in S star M is picking a point on the base manifold M and the direction. So you pick a point in the vector on your, say, 3 manifold. And then you have to pick an unstable direction. So it's a perpendicular one. So you're picking a point in 2 perpendicular directions. And once you have this, you find yourself, actually in dimension 3, you find yourself on the frame bundle. And so there is a natural flow on the frame bundle which would correspond sort of unstable in these directions. And so you go to the frame bundle, you have this natural horacyclic vector field, and then you apply Ratner theory to that. And that's what it ends up being. And you can also see it's sort of a point in 2 directions, so the idea is that if you try to close a surface through those points, is it going to close up or not? If it closes up, then you have a problem. Okay. So I have a tiny bit of time left, apparently. Do I?
2 minutes, yeah.
Okay. 2:20, okay. So I'll mention a few things, maybe more orally. So here, I wanted to stress that theorem because it's recent and sort of appealing. There is a slightly older theorem by myself, Arthreya and Miller, which I will not write here, but I'll tell you how to adjust it. So what we did is we dealt with complex hyperbolic quotients, and the abstractions were given by compact, immersed, totally geodesic complex submanifolds. And the upshot of that was that in complex hyperbolic manifolds, the situation in some ways is actually easier, because for a complex hyperbolic manifold, you have a fast unstable direction, which is 1-dimensional. The expansion rate is 2. And then you have slow unstable directions, which are, they have a lot of dimensions. The expansion rate is 1. And we showed that you can adjust this argument and sort of put all the slow directions into things you're folated by, if you adjust it right. And so you only need the argument in the fast unstable direction, which is 1-dimensional, so 1-dimensional fractal uncertainty principle can be used. Now, the remaining less than a minute, I will mention a little bit something what happens in the case of quantum catmaps. Just show that the situation is actually complicated. So I stand by the conjecture, and QE might as well be true. But there is this toy model of quantum catmaps, which is a different setting, but with a lot of similarity, where a lot of things are actually not true. And so the idea here is that my geodesic flow is replaced by the catmap action of an integer symplectic matrix. And so what's known is Quantum unique ergodicity fails in this setting. There's a famous counterexample of 4 nanometer dB error. So for d equals 2, QE fails. But the support of every semi-classical measure is still the full torus. So their counterexample had full support. And that's a result by Near-Schwarz. Yes?
1. D equal 1.
D equals 1, I'm sorry. That's right, so two torus. And then in higher dimensions, QE can fail in other ways. So we can have support of mu, which is Lagrangian subtorus. And that's A invariant Lagrangian subtorus. So symplectic structure matters. And that's a counterexample that's, I learned about it from Stefan, who sent me to a paper by Kelmer, which references a private communication with Stefan Nonnenmacher as a source of that. So it's somewhere between the two. So there is this family of counterexamples. But the more recent results, due to Kim and Anderson and Lemke Oliver, is that, I'll just give you a counterexample. So you can actually have the support of the measure as a union of two symplectic subtori. Proper symplectic subtori. So at first we thought that you can only live on a Lagrangian subtorus, and then Elena managed to prove that you cannot have the support of a measure on a single symplectic subtorus. The idea is that the uncertainty principle prohibits a quantum state from being localized on a symplectic submanifold, but it doesn't prohibit localization on a Lagrangian submanifold, so that's the intuition. And then she was able to show that for a generic ket map, the support is everything, but she was also able to construct counterexamples by sort of twisting the 4 nanometer dB error counterexample correctly to show that you can have examples of semi-classical measures which live in a union of two transversal symplectic subtori. And if you try to follow this argument, you would exactly reach the failure of FUP for two perpendicular lines. So in the Stoy model, this counterexample does actually occur. Okay, I'm sorry I ran over. Thank you for your attention.
Thank you very much, Semyon. Further questions, comments?
In dimension 2, would it still be possible to prove a similar result for the support of semi-classical measures, but for Schrödinger operators?
Right, so the question was, sorry, okay, there you go. I put the chalk back, it's all neat now. Yeah, so the Schrödinger operator question, you can do it in two ways. So you can throw in lower order terms, and as you saw already in the talk on Tuesday as you will see in Gabriel Rugger's talk, sometimes lower order terms matter, but here they don't. It's a principal symbol statement. So if you just add Laplacian plus v, you're going to get the same result. We didn't write it up, but it's sort of, there's no difference. In fact, it sort of follows from the quasi-mode estimate we have. And you could even take a self-adjoint vector field perturbation and, you can make it work. If you make it principal, so if you take Laplacian plus lambda j square, then I think it will still work under the Anosov assumption. It will be a bit more painful because it's sort of, you'll have a family of operators and not an operator itself, but yeah. So really what matters to us is the Anosov assumption and dimension 2. I think as long as this is true, we can make things work. Yes, Jared.
I'm curious about your somewhat careful statement of that conjecture and Zev's earlier question. Is it the case that the community is converging to thinking that QUE fails, but the support is everything? Is that?
No.
I don't think so. I mean, I don't speak for the community, but I personally think QE is true, but I have no idea how to prove it. But for quantum ket maps, it does fail in a variety of ways. So, if you're trying to prove QE, you have to rule them out, among other things. Yes?
Just a couple of questions. So the first one, imagine you prove that your position manifold has a constant negative parameter, but you didn't use this proof of the idea.
Oh, that's another theory, among other things.
So the first theorem that I stated and I erased, we did it in constant curvature first, and then we managed to do it for variable curvature surfaces, which was considerably harder. And I didn't explain at all why. So in my sketches, I focused on the constant curvature case, but we can do it for variable curvature in dimension 2. In higher dimensions, so far, we can only handle locally symmetric spaces. And it has to do, one of the major difficulties already in dimension 2 is that the stable unstable foliations are not smooth the way they depend on the base point. That's one of the very, very nasty things you have to fight. And in higher dimensions, they're even less regular. There are others. Yes, maybe I'll, yes.
So
and then we can come
in
back
this
to
sort of push forward, so you take an unstable leaf, you apply the geodesic for time t, and then you get this stretching of the leaf. But since you take time, which is log of 1 over h, doesn't this sort of porous condition will sort of this mu will decrease as h goes to 0?
Right, so you don't apply this to mu. So you start with okay, so the way the argument works, and that's also already present in, say, Untitled non-inertial works, you start with macroscopic information. Say my measure is small and a fixed open set. That's macroscopic information. And then you refine it up to logarithmic time, and so you get microscopic information about how the eigenfunction lives. Which is, it's far from trivial how to do it, but sort of the original paper of Untitled shows how this can be done. And then you apply the uncertainty principle to this. So you apply it to localization. So here my I can be a very small interval, almost size h, really c times h if you want to be pedantic. And then I might propagate up to time log 1 over h to sort of see the whole. No, you can stop it now if you want.
No, you're...
It's been over.
All right, so I suggest we postpone further questions
Okay.
for the coffee break.